Okay, so last time, um, so ganito itong na-discuss last time class. Nung to na humano? Okay, so last time, from this equation, E is equal to, so we know that E can be expressed as the negative gradient of the potential. So from the divergence of the electric field, so the divergence of E leads us to this equation, and this is the Poisson's equation. Okay, Poisson's equation, and we also have this one. So if the charge or there is no charge in the region, then rho is equal to 0, such that uh, we have the Laplacian of V is equal to 0. So we call this the Laplace equation. Okay, now we see that from the Poisson's equation, it gives us rho. It gives us rho if we know B. But we don't really need rho, but ang atong kinahanglan is kining potential. Since out of the potential, we can then get the electric field. Okay, so inverting the Poisson's equation, we will obtain this one. So we have V of r is equal to 1 over 4 pi epsilon naught integral of rho over r d tau. So this is for volume. And then for surface, we have V of r is equal to 1 over 4 pi epsilon naught integral of sigma over r dA. And then for line charge, we have 1 over 4 pi epsilon naught integral of lambda over r dl. Okay, so this is, we can get these expressions assuming that our reference point is at infinity. Okay, so for example, for the spherical shell that we had last time, so naka-spherical shell, no? Kung sa ganyan spherical shell, hollow siya sa sulod. Okay. And then we want to know the potential at this point, P. So this is a point that is directly above from the center of the shell, and the distance between the point and the center of the shell is z. Okay, so for this, so this is our y, from y, so z axis, y, and then this is your x. Okay, so for example, if we take a small area here in the surface of the shell, then this is our r. So this is the length from the center, of course, to the surface is equivalent to the radius of the shell. And this one, from the surface na atong i-consider padulong sa point, this is, sorry, okay, so this is your r, the separation vector r, and this can be obtained using the cosine law. So we have your r squared is equal to r squared, finish ano? R squared plus z squared minus 2r z cosine theta, where theta is this. Ano siya? Ano siya nga length? Padulong sa imo ang kung siya nga line diri ang. Okay, so this is your theta. So that your V of r is equal to 1 over 4 pi epsilon naught integral of sigma over r dA. Okay, now take note that your dA for a spherical shell, your dA, if you take a small infinitesimal area in the surface, your dA is equal to r squared sine theta d theta dphi. And we have a constant r, so your r is just equal to the radius of the shell. Therefore, your dA can be written as r squared sine theta d theta dphi. Okay, so substituting, we have your V of r is equal to 1 over 4 pi epsilon naught. We can actually take sigma out of the integral since it is a constant. So we have sigma. And then inside we have your dA is r squared sine theta d theta dphi. And your r is equal to the square root of r squared plus z squared. Now, you have to take note, class. This is your r squared. Nakuha na siya na to through the cosine law since we cannot use the Pythagorean theorem for this. Kaya nga gani, this is your right triangle. So we have r squared plus z squared minus 2rc cosine theta. Okay. So evaluating this, we can actually take r squared out of the integral since it is also a constant. So we have sigma r squared over 4 pi epsilon naught. And then we also know that the integral of sine theta, we cannot evaluate sine theta d theta since we have a theta in the denominator pa. So we can we can evaluate d phi immediately since wala may laing phi diri sa integrand, no? We know that the integral of d phi is equal to 2 pi. And then we are left with this. Okay, sine theta d theta divided by the square root of r squared plus z squared minus 2r z cosine theta. Cosine theta. Okay, so for this, we can actually cancel this. Pwede natin i-cancel ni si 4 pi and then also this 2 here. So we are left with, you have sigma r squared over 2 epsilon naught. Okay, and then for this, for the integrand, we let u be equal to, kining naa sa sulod, no? R squared plus z squared minus 2rz cosine theta. So that du is equal to 2rz. You have negative sine theta, or this is just sine theta. 2rz sine theta. Such that your sine theta d theta is equal to du over 2rz. Okay, so substituting this, so we have your sine theta d theta is now equal to du over 2rz. And then we have here, since we let this to be u, then this is equal to, the denominator is equal to u raised to the power of 1 half. And then here you have du over 2 or z. Now you have to take note that, sorry, this is du. You have to take note, class, that z here is a constant. It is the length from the center of the radius towards your point P. And then r also is a constant. So this will now become sigma r squared over 2 epsilon naught. And then we will take 2rz here. Outside the integrals, we have 1 over 2 rz. So what is left is the integral of uh, du. You have u raised to the power of minus 1 half du. Okay. So sa integral ani, we have sigma r squared over 4 epsilon naught rz. And then this is u to the 1 half over 1 half, right? Ito ba, class? U to the 1 half over 1 half. Or we can rewrite that as we can have this one. This is equal to 2 multiplied by, so you have your 1 half here. 2 multiplied by sigma r squared. Sigma r squared divided by 4 epsilon naught rz. We have 4 epsilon naught rz. And then what is left is your u raised to the power of 1 half, or this is just equal to the square root of r squared plus z squared minus 2rz cosine theta. And then we evaluate this one. We will be evaluating this one from 0 to pi. Okay. So evaluating this one from 0 to pi, we can actually cancel this r here. So we are left with this. We can also cancel this out. So we are left with sigma r over 2 epsilon naught z. And then evaluating this from 0 to pi, we have cosine pi. Pilam cosine pi, class. We have r squared plus z squared minus 2rz. Cosine pi is equal to -1, so this will become positive. Okay, minus the square root of r squared plus z squared, and then you have 2rz cosine 0. So this is -2rz. Okay, we can further simplify this one. We have sigma r over 2 epsilon naught z, and then we can actually have the factor of this. So we can write r plus z squared. So this is equal to r plus z squared. While the other one, this one, this is equal to the square root of r minus z squared. And then we have to get the positive root, take the positive root. We have sigma r over 2 epsilon naught z, and then the square root of this one. So we can just write this as r plus z. And then this one, this term here, we have to take the positive root. You have to take note that your z is greater than r. So based on the figure, the point is outside the shell. So it must be that your z, the length from the center towards the point, is greater compared to the radius r. Therefore, the positive root for this is equal to, yeah, it's um okay. So this is for points outside the shell. So this is equal to sigma r over 2 epsilon naught z. And then from here, we can cancel out, ito cancel out to the class, z, no? So we have 2r. So for points outside the shell, we have this one. And the potential is equal to V of r is equal to sigma r over 2 epsilon naught z multiplied by 2r. Or we can further write this as, cancel na to ang 2, no? So we have sigma r squared over epsilon naught z. Okay. So this is the potential outside the shell. For points inside the shell, we have this one. So from here, there is no kining expression in class. We have to take the positive root. So for points inside the shell, your r is greater than z. So the positive root is r minus z. So we have v is equal to sigma r over 2 epsilon naught z. And then we have r plus z minus r minus z. Okay, let me just verify. So we have sigma r over 2 epsilon naught z, and then we have r plus z minus the positive root of this one is r minus z inside the shell. Therefore, we have this v of r is equal to sigma r over 2 epsilon naught z, and then we can cancel r out, so we are left with 2z. Or this is just equal to sigma over epsilon naught multiplied by r. Okay. So again, this is inside the shell. The potential inside the shell. So take note that uh, even though there are no charges inside the shell, dili zero ang potential class. Now, we can actually express this in terms of Q. Expressing this in terms of Q, noting that, so take note that Q is equal to sigma A, or this is equal to sigma times 4 pi r squared. Okay. So we have uh, V inside. So your V inside, we know that it is equal to R multiplied by sigma over epsilon naught. So we can rewrite this as R over epsilon naught Q over 4 pi r squared. Or this is just equal to Q over 4 pi epsilon naught R. So this is familiar. And for V outside, we have r squared sigma over epsilon naught z. So we can rewrite this as r squared. Your sigma is equal to q. Take note that your sigma is equal to q over 4 pi r squared. So you have epsilon naught z, and then you have q over 4 pi r squared. So we have here okay, this is outside, so this is your big R here. We can cancel this out. We have q over 4 pi epsilon naught z. Okay, so this is for points outside the shell in terms of q. Okay, so far we have learned about the fundamental quantities of electrostatics. We have rho, electric field, and then we have the potential. And we have derived all 6 formulas interrelating them. So let us recall those 6 equations before we proceed to our next topic. So the relationship between rho and V. So you have this, V is equal to 1 over 4 pi epsilon naught, integral of rho over r d tau. or we can use this equation. So if we know V, we can get rho. So we have the Poisson's equation equal to negative rho over epsilon naught. And then equations relating E and V. So we have this. E is equal to the negative gradient of V, and then we have V is equal to the negative integral of E dot dl. And then we also have equations relating rho and E. So we know that your E is equal to 1 over 4 pi epsilon naught integral of rho over r squared, r hat, d tau. And then we also have the divergence of E, which is equal to rho over epsilon naught. This is the differential form of Gauss law. And then we have this one. The curl of E is equal to 0. Okay, so now we proceed to work and energy in electrostatics. Okay, energy. So for example, you have a stationary configuration of source charges. You have this configuration of charges from Q1, Q2, Q3, Q4, Q5, and so on. So these are your source charges. And then you want to place another charge here near the assembly. So from, say for example, from infinity, you want to place another charge here. So the question is, pila ang amount of energy ang kinahanglan in order to move this single charge here from a certain point padulong diriya. Okay? So we know that kung naa kay charge, mag-emanate na siya og electric field. And because of that field, na ay force, electric force. Kung naa kay duha ka charges or yeah, at least two charges na mag-interact, na sila'y force, which can be quantified using the Coulomb's law. So as you move closer towards this configuration, according to the inverse square law of katong Coulomb's, it is proportional to 1 over r squared. 1 over r squared. The more you get closer to this configuration of charge, mas dako ang force na imong experience. So kailangan o energy in order to counteract that force. So for example, if kini siya ang configuration of charge diri kay positive, and then ang imo ang charge nga i-move from this point padulong diri is also positive, then most likely, of course, mag-repel sila, no? So unsa ang amount of energy ang kinahanglan para mabutang nimo ni siya nga charge diri aning duol aning configuration of charges here sa imong source charge. Okay. So we can actually quantify that one. It is equal to we have this one. We know that from mechanics class, we know that work is equal to the dot product of force and the displacement. Okay. So we have here, see work. We can express force here as the electrostatic force which is equal to Q times the electric field. Okay. So we have Q times the electric field dot with uh, the infinitesimal length dl. So we have this one. Now take note that this force here na kinahanglan nato is in opposition to the electrical force due to this configuration of charge and kini mong charge. Okay, so this should be negative. So W is equal to the integral of Q E dot dl, or we start with F equals the integral of F dot dl. So it is a line integral. And then F here is the force that is needed in order to counteract the force due to these uh, charges. So we have a negative uh, force here minus Q E, and then we can actually take Q out of the integral sign. So we have negative Q integral of E dot dl. And we know that E dot dl is just equal to, so ganun siya, this is just the potential. So if this is from A to B, yeah. So if this is from A, so kini siya nga point is from A, and then this point here is B. So we have here A to B. V B minus V of A. Since we know that E dot dl, integral of E dot dl from A to B is equal to the negative V of B minus, sorry, this is the negative of VB minus V of A. So we have here, so if E dot dl is equal to negative V of B minus V of A, then this one is, yeah, this is negative also. So we have the work that should be done in order to move this charge here towards point B is equal to Q times V of B. Sorry. Ito ba? Positive na siya, no? Minus V of A. Or the potential, or we can have another definition of the potential here. So from this, we will have, you have Q, the work is equal to QV of B minus V of A. So we can write V of B minus V of A. The potential difference, this is actually the potential difference, is equal to W over Q. Okay. So this is the potential in terms of all right. So in other words, or we can say that the potential difference between points A and B is equal to the work per unit charge required to carry a particle from A to B. So the potential difference between points A and B is equal to the work per unit charge required to carry a particle from A to B. Or you can just say potential is work per unit charge, energy per unit charge. Okay, so for example, if we want to know the amount of work or how much work would it take to assemble an entire configuration or collection of point charges, how much work would it take to assemble an entire configuration of charge? Okay, so for example, we have uh, three charges, point charges, and then we want to assemble it such that it fits here. Okay, so from infinity, you can say infinity class, and then we want to assemble it in such a way nga mura siya ing ani og form. Say for example, this one. Let us start with point charge 1 with charge Q1. So let us bring these point charges one by one from infinity. So the first charge takes no work. Kaya naman, wala pa may field, no? There is no field yet to fight against. So Q1, kung ibutang siya na to diri the work done is equal to 0 since wala pa may field. How about Q2? So for Q2, say for example, we want to place it here. So diri na si Q2. So since na naman si Q1 diri a class, nanay field. So the work that should be done is equal to Q2 multiplied by the potential due to this charge here. So take note that this potential here is the potential due to Q1. Potential due to Q1. And then suppose the distance between Q1 and Q2 is R sub 1, 2. Then this is equal to Q2 multiplied by 1 over 4 pi epsilon naught. You have Q1 over R1, 2. Okay. So take note that this is the potential due to Q1. Or we can rewrite this as 1 over 4 pi epsilon naught Q1, Q2 over R sub 1, 2. Okay. So this is the work. And then lastly, we place Q3 here. So what will happen? So unsa nga pila ang work na kinahanglan in order to assemble Q3 here from infinity padulong diri ah. So we now have duha ka fields, no? Fields due to Q1, field due to Q2. So in order to bring Q3 padulong ani nga uh, location, so we have Q3, the work done is equal to Q3 multiplied by V sub 1. So this is the potential due to Q1 plus the potential due to Q2. Okay, so this is equal to Q3 multiplied by your V1. This is equal to 1 over 4 pi epsilon naught Q1 over R12. And then suppose this is R13. The distance between your Q2 and Q3 is R13. So we have 1 over 4 pi epsilon naught Q3. This is Q2 over 4 pi, sorry, R13. Okay. Or in general, if we have daghan kay nga charges no nga i-assemble, we have this general expression. So we have work is equal to 1 over 4 pi epsilon naught summation of, you have Qi multiplied by Q sub j over Ri. Okay. Take note that your I is from 1 to n, and also your j. Your j is equal to 1 to n, where j should always be greater than I. Okay, do you have any questions, class?
None so far, ma'am.
Okay, we have another example here. So how much work does it take to bring in another charge? To bring in another charge from infinity and place it in the fourth corner. Okay, so we have ini siya ang configuration class. So we are given with Q1 is equal to negative Q, and then your Q2 is equal to plus Q. Ah, So, nadali si Q2, in a corner, is equal to plus Q. Your Q3 is equal to minus Q. Okay. And then we want to place the charge here, the positive charge here. You can say infinity. Okay. And then the distance between this Q1 and Q2 by A also. So this is also A. Square siya atong configuration. Okay.
Alas 12 na. Alas
So for this, we just have to account the individual contribution of the charges. So we have Q, your plus Q here multiplied by the potential due to the charges. So we have V sub 1 plus V sub 2 plus V sub 3. Okay. So work is equal to plus Q. Then you have 1 over 4 pi epsilon naught. Your Q1 is positive Q, A divided by A, plus 1 over 4 pi epsilon naught Q2 over A square root of 2. So, how many siya gikan, class? So, the distance from Q2, padulong diri nga point, if this is the side diri kay A, this is also A, then this is equal to A times the square root of 2. So you can use the Pythagorean theorem to solve this one. And then lastly, we have Q3 over A. So we can take 1 over 4 pi epsilon naught out. So we have Q over A, and then your Q1 is negative. Your Q2 is positive Q over A square root of 2. And then your Q3 is negative. So minus Q over A. So this is equal to Q over 4 pi epsilon naught. You can take all the Q's. This is actually Q squared. And then we are left with minus 1 over A. So this is minus 2 over A. Sakto ba? Minus 1 over A plus minus 1 over A, you have negative 2A plus 1 over A square root of 2. You can further simplify this one. You have Q squared over 4 pi epsilon naught. And then, combination of the class. You can take A out. So we are left with negative 2 minus 1 over the square root of 2. Since these are just constant, pwede na siyang tumaad. Pila man siya, class? Do you have your calculator with you? Negative 2 minus 1 over the square root of 2. So you have Q squared over 4 pi epsilon naught A. And then, kini siya nga number. Pila ni siya apelyirin?
Negative 4 minus the square root of 2 over 2, ma'am.
Negative 4. Negative 4 point
Minus square root of 2
minus square root of 2. Pwede,
over 2, ma'am.
over 2. All over 2.
Yes, ma'am.
Okay, you can choose to express this one as ing ani or pwede man ni siya mga kuan class. Number lang ni siya, no? Alright. Now, how about this one as your seat work? So, how much? Let us go back to the figure. So, kini siya nga figure class. Pila ang amount of charge nga kinahanglan para ma-assemble ni siya nga collection of charges? Okay, so find the total work done in order to assemble kini siyang collection of charges. So nakuha na ninyo ang paano katong Q4. So take note that this is negative Q, positive Q. This one is also positive Q. This one is negative Q. And then the side of, or sorry, the distance between the 4 ay A. Okay. So you have to submit this today. All right. So Wednesday class will continue with work and energy. And then, ang recording na to is katong conductors. Okay? So, until diha lang kataman for this semester. Okay, we will finish chapter 2 and then we will continue this sa sunod nga semester. Okay? So, please make sure to submit 2 assignments. I think katong inyong assignment last time, naka-answer na ba mo ato? Nakalimot mo ato. It's problem 2.1.